Hi everyone, welcome back to my YouTube channel. So today we are going to solve day 24 problem of this month on LeetCode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now, without any delay, let's get started with today's problem. Problem number 802, find eventual safe states. Okay, and this question is very important. Okay, and this question is asked in Microsoft. All right, so let's read the problem statement first. There is a directed graph of n nodes with each node labeled from 0 to n minus 1. Okay, so 0 to n minus 1 we have nodes. The graph is represented by a 0 indexed 2D integer array graph. Okay, where graph of I is an integer array of nodes adjacent to node I. Okay, meaning that there is an edge from node I to each node in graph of I. Okay, so let's suppose this is a graph, okay, given to us, and here there are some values given to us, right? So let's say this is index 0, this is index 1, and so on. Okay, and here at 0 we have, let's suppose we have node 2 given to us, node 3 given to us, and here we have node 4 given to us, 4 5 given to us. Okay, let's say, so what does this line mean? This line means that from this 0, okay, which is index, from this 0 node we have directed path to 2, we have directed path to 3. From this one, we have directed path to 4, we have directed path to 5. Okay, so the graph is represented by a 0 index 2D integer array graph, where graph of I is an integer array of integer array of nodes. Graph of I is integer array of nodes adjacent to node of I. Okay, meaning that there is an edge from node I to each node in graph of I, 0 to 2, 0 to 3. Okay, that's the meaning of this line. All right. Now, a node is a terminal node. Okay, if there are no outgoing edges. Okay, so let's suppose there is one node. So from this node, if there are no edges, okay, or there are just incoming edges, okay, then it is going to be my terminal node. Okay, there should be not be any outgoing node from this. Okay, then it is not a terminal node. Okay, so a node is a terminal node if there are no outgoing edges. Okay, clear? A node is a safe node if every possible path starting from that node leads to a terminal node or another safe node. Okay, so this is what we need to find. Okay, so this is the definition of terminal node and this is the definition of safe node. So from safe node we are going to traverse and we will see if we can reach to every terminal node. Okay, from every path we reach to a terminal node. Okay, if every possible path, okay, this is important words, every possible path starting from that node leads to one terminal node. Okay, a terminal node with no outgoing edges. So we have to return an array containing all the safe nodes of the graph, and the answer should be sorted in ascending order. Okay, so our answer should always be sorted in a ascending order, right? So we have given a directed graph. Okay, so I hope that you guys are clear with the problem statement. All right, so now here if you see this example number 1, okay, so this 0 1 2 3 4 5 and 6. Okay, so from 6 there are no outgoing edges, from 5 there are no outgoing edges, from 4 if you see we have outgoing edge to node 5. Okay, so see 4 to 5 there is one a link, right? This one. All right, then from 3 we have edge to 0. Okay, so 3 to 0, so see this. All right, then from 2 we have to 5 go to 5. Okay, so see this. Then from 1 we are going 2 and 3. Okay, so these two. And then from 0 you can see we are going to 1 and 2. Okay, so I hope that you guys are clear. All right, so here you know that this is going to be one safe node. Okay, this is terminal node now, right? There are no outgoing edges from this one, there are also no outgoing edges from this one, so this is also safe node. Now if you see this 4, from 4 you can go to 5. Okay, there is just one path, 4 to 5, so this is also safe node. Okay, 4. Then if you see this 2, from 2 there is just one outgoing path, 2 to 5, then 2 is also safe node. Okay, and we are storing the result in sorted order. Okay, but for other example, like from 0 if you see, so 0 to 1 you go. Okay, then 1 to 2 if you go. Okay, then 2 to 5 you go. This is one valid path. Okay, so here let's suppose 0 to 2 you go. Okay, then there is also one valid path. Okay, 0 to then 5. Okay, but if you go to 0 to 1. Okay, now see this. I will go over this in much detail later on, but first let's see. 0 to 1 if you go, then 1 to 3 if you go, and then 3 to 0 you are going back now, right? So this is one cycle. So we have to make sure that every possible path lead to a terminal node. Okay, every possible path starting from that node leads to terminal node. So this is not possible. Here there is one cycle, right? So that is why we are not adding 0 in our output, right? So the given graph is shown above. Node 5 and 6 are terminal nodes as there are no outgoing edges from either of them. And every path starting at node 2, 4, 5 and 6 all lead to either node 5 or 6. Okay. So I will give a much better visual representation of this diagram in later on. Okay. So but first here I just want to show you that there is cycle. Okay, then we are not going to add that in our output. Okay, so here where I am leading with this, so we are leading to the topological sorting. Okay, we have to find the cycles, okay, in a directed graph, right? So that simply means which algorithm? Kahan's algorithm. Okay, so what is Kahan's algorithm? Okay, so let's read this first. Okay, so if you guys don't know about this, let's read it. Okay, so Kahan algorithm is a topological sorting algorithm that works for directed acyclic graphs. Okay, so this is directed acyclic graph. Okay, it uses a queue based BFS approach to process nodes with 0 in degree. Okay, so in the queue I'm going to add all the nodes with 0 in degree first. Okay, 0 in degree, then the algorithm repeatedly removes nodes with 0 in degree from the graph and reduces the in degree of their neighbors. Okay, so this is just a definition. Okay, so just go over this definition. Okay, read it one more time, okay, by yourself. All right, so now what are the steps of Kahn's algorithm? All right, so first we have to calculate the in degree. For each node we have to count the number of incoming edges. In degree means incoming edges. Okay, then we have to initialize queue. In the queue we are going to add all the nodes with a 0 in degree. Okay, then we have to process the queue. While the queue is not empty, we have to remove a node from the queue. Okay, we are going to process it, add it to the result. Okay, topological order or a process nodes. For each neighbor of the removed node, okay, neighbor of the removed node, we have to reduce it in degree by 1. Okay, and if any neighbors in degree becomes 0, then we have to add that in queue, otherwise not, right? And if all the nodes are processed, the graph is DAG, okay, directed acyclic graph, otherwise there are cycles. So if starting from this 0, okay, if there are any cycle, then we are not going to add that in our output. If starting from this 4 there are any cycle, no. Okay, so then we are to add that 4 in our result, right? So this is what we need to do. Okay, so Kahn's algorithm is beneficial for us, okay, in this case. So what are the applications of this algorithm to this particular problem? So in this problem what we are doing, we are finding the safe nodes in a directed graph, right? Safe nodes are the nodes that cannot lead to cycles in any path. All right, which is equivalent to nodes in the reversed topological order. Okay, so I will also show you what is this reverse topological order. Okay, why we have to reverse the edges, okay, from this to this. Okay, why? All right, I'm going to show you with example. Okay, I'm going to prove it why it is necessary. Okay, here's how this algorithm can be applied. So we have to reverse the edges in a graph to process nodes based on their influence. Then we have to compute the in degree of each node in the reverse graph. Then we have to add all the terminal nodes with 0 in degree in the reverse graph to the queue. Then we have to process the graph. Okay, remove a node from the queue, add it to the list of the safe nodes. For each neighbor in the reverse graph, reduce its in degree by 1. And if neighbors in degree becomes 0, then we have to add that in queue. Then in the end, we have to sort the result. Okay, the nodes in the result list are safe nodes. Okay, sort them to meet the problem's requirement. All right, so now let's see why we have to do reverse and all that stuff. Okay, so initially if you see, this is my example number 1. Okay, this is my example number 1 only. This one, okay, 1 2 2 3. Okay, this one, this example. Okay, so here if I give the index in here 0 1 2 3 4 5 and 6. Okay, so from 0 node we can go to 1. Okay, so I can draw this, and we can go to 2. Okay, from 1 we can go to 2. Okay, and we can go to 3. All right, from 2 we can go to 5. Okay, from 3 we can go to 0. Okay, and from 4 we can go to 5, and from 5 from 5 we can't go anywhere, from 6 we can't go anywhere. Okay, so in degree, first let's in degree, okay, without reversing it. I'm not reversing it yet, so let's write the in degree. Okay, so in degree for this is 0. Okay, in degree for this is 2. Okay, two nodes which are incoming. In degree for this one is 0. In degree for this one is 1. In degree for this one is 1. In degree for this one is 1, and in degree for this one is a 1. Okay, right. Double check one more time. 1, and here also 1. Here this 1, here it's 1. Okay, here it's 1. All right, 2 here. Okay, so if I don't reverse, okay, so what you are going to do, uh, by applying Kahn's algorithm, you are going to add the nodes with 0 in degree first. Okay, so we have 4 and 6, so you are going to add them to queue. Then you are going to process 4. Okay, so 4 is going to 5, and now 5, if 4 is going to 5, so 5 is in degree, I am going to subtract it with 1. Okay, we have to subtract the neighbors in degree. Okay, so it still didn't become 1, or still didn't become 0. Okay, and we have processed this completely. Okay, 4, so in my output I have added 4. Okay, let's say. Then I'm going to process 6. From 6 there are no outgoing edges. Okay, so it will remain as it is. Okay, so I have added this 6. So now I am starting from terminal nodes. Okay, from 5, there is no 5 here. Okay, I can't go anywhere else. So how I'm going to find the cycles? Because here I'm starting from the nodes with 0 in degree. Okay, from the terminal nodes itself. Okay, in the starting only. So I can't find out any cycle. Okay, so there is no possibility of finding the cycles, right? Because I am starting from the nodes with degree which itself is 0. Okay, in the starting, right? So here if you see from and in this problem statement, what we have to find the safe nodes. So I am starting itself from the safe nodes, right? How can I detect the cycle, right? There is no way to detect a cycle if I'm starting itself from my start nodes, in which there is no outgoing. Okay, in which there is just in degree 0. Okay, so 6 is a safe node, 4 is also one safe node only, right? 4 to 5, then 5 there is nothing. Okay, we can't go anywhere. Okay, so we stuck here. We are not able to find any cycle, right? Right, so this is my output. No, and here, see, why reversing will work. Okay, so if you move like this, okay, here to here, here, so this is same as like this now, so definitely you can reverse it. Okay, you are just finding the cycle. So here there is one cycle like this, so here there is one cycle like this, no issue, we just reversed it. Okay, so here in the problem statement we have to find the safe nodes, and we are starting from the safe nodes in the starting itself. Then how we can detect any cycle from other nodes? Not possible na? So we have to reverse it. Okay, so now let me do one thing here. Let me just erase this. Okay, now integers are going to be changed. All right, this is done, and here let me just remove it. This one, this one, this one, this one, and here these three. Okay, that's it. All right, so now let's change it. Okay, so 4 to 5 now, so let's change it to I'm using this blue color, so now I have to change it to like this. Okay, this arrow. Okay, reverse, delete it. Then 2 to 5 now, I'm going to change it, making it 5 to 2. Okay, I'm reversing it. All right, and here 1 to 2. Okay, I'm going to remove it. Okay, this 1 to 2, I'm going to make it 2 to 1. All right, now here 3 to 0, I'm going to make it 0 to 3. Okay, reverse it. Then here 0 to, I'm going to make it 2 to 0. All right, here 0 to 1, I'm going to make it 1 to 0. Okay, and then here 1 to 3, I'm going to make it 3 to 1. Okay, so now write in degrees. So here it's 0, and here it's 0, here it's 1. Okay, I reverse it. So here for this 2 in degrees 1, for this 3 in degrees 1, for this 1 in degrees becoming 2, for this 0 in degrees becoming 2, and that's it, right? This is done. Now same thing. Okay, just apply Kahn's algorithm here. So first write the nodes with 0 in degree. So 5 and 6. Let me use white color pencil now. 5 and 6 we have added. Okay, so now first let's process 5. Okay, so 5, what are the neighbors of 5? 5's neighbor, one is 2 and one is 4. Okay, so let's first process this 2. Okay, so I am processing this 2. So now if I am processing this 2, so this 2's in degree will become 0. Okay, I am going to process it, and if it's in degree becoming 0, I'm going to add that in my queue. Okay, this is what I'm processing. Okay, I pop this element, remove this element from queue. Okay, and from 5 there is one more neighbor 4. So 4's in degree is going to become 0, and I'm going to add this 4 here. This is done. Okay, so 5 I have completely processed. So in the result I'm going to add this 5 here. Okay, then I'm going to process this 6. For 6 there are no neighbors. Okay, nothing. So I'm going to add 6 here. All right. Okay, then I'm going to process this 2. Okay, processing this 2. So 2's neighbor is this 0. Okay, so this 0's in degree is going to become 1 now. From 2 it is going to become 1. Okay, and there is just one neighbor for this 2. Okay, and here for 0 in degrees doesn't become 0, right? So I'm not going to add this one here. All right, now let's process 4. So 4's in degree is already 0 and there are no neighbors. Okay, so 4 is going to be added to here. Okay, so last time we have added 2 and now this time we are going to add 4. Okay, so this is my output. Result is 2 4 5 6. Okay, and all others, see, here it is 1, here it's still 2, here it's still 1. Okay, so when I process this 2 now, 2's neighbor is this one also now, so this is also going to become 1 only now. Okay, so nothing will become 0. Okay, so I not added anything. Okay, so in the end the result is 2 4 5 6. So if you see here 2 4 5 6. Okay, this is what we need to write. Okay, so the remaining ones in all these nodes, if you're going to start, you will find one cycle. Okay, so I hope that you guys are clear. Okay, cycle is there. All right, so now let's write the code. Okay, so I hope that you guys are clear with algorithm. Okay, now let's write the same story what I have explained here. So first thing what you need to do here, let's calculate the number of nodes in my graph. Okay, so that's is equal to int n is equal to graph dot length. All right, now create one array list. Okay, here array list is going to contain integers. Okay, and here result, let's name it as result, new array list. Then we have to create a reverse graph. Okay, so we have to reverse the graph now. So create one list of integer, and here name it as reverse graph. Okay, is equal to new array list. All right, and then just iterate over all the nodes one by one. Okay, for int I is equal to 0, so I is less than n, I plus plus. Okay, all the nodes I'm going to iterate, and I'm just going to create one array list in front of them. Okay, so reverse graph dot add, okay, new array list. All right, this is done. Okay, so now we have to track the in degree. Okay, so create one array, okay, to calculate the in degree of all the nodes. Okay, in degree is equal to new int total number of nodes. Okay, so 0 to n minus 1 we have to write now, so total n. So now just iterate int I is equal to 0, I is less than n, I plus plus, and here just iterate over all the neighbors. Okay, int neighbor in graph of I. Okay, so first graph of I. All right, here. Okay, so it is like this. So this, okay, this one. All right, one second, this one. Okay, 1 and 2. So now for 0 we have this 1 and 2 now. So from 0 we are going to 1 and 1. From 0 we are going to 2 also. So I'm just going to reverse it. From 1 we are going to 0, from 2 also we are going to 0. Okay, so that is what we did here now. From 1 we are going to 0, right? So see, we reverse this, and from 2 also we are going to 0. Okay, so now what I have to do here, reverse graph, okay, dot get neighbor, okay, and here in that neighbor, okay, I'm just going to add my current I. Okay, so we are creating the reverse graph now. So here 1 to 2, so from both we are going to 0. Okay, so here we have already created one array list, so in that we have to add just 0. Okay, something like that. So this is what we have to do. Okay, so same thing you have to do for other nodes also, and we have to update the in degree as well. So in degree of I, okay, so it is going to be incremented. Okay, in degree of 0 is going to be incremented. So here in degree of this is going to become 2 now because of this 2 and 1. Okay, so 2 times we are going to increment. Okay, so this is done. So we have calculated the in degrees, and we have created the reverse graph as well here. Okay, in this step, that's it done. Now we have to start with nodes having no outgoing edges. Okay, in degree is equal to 0 in the reverse graph, and we have to add them in queue. Okay, that is what I am doing in the while explanation, right? So same story right here. Okay, queue integer q is equal to new linked list. All right, and then we have to write one loop for int I is equal to 0, I is less than n, I plus plus. Okay, and here if in degree of I, okay, if it is equal to 0, then in that case we have to just simply add that to our queue. Okay, queue dot add I. All right, done. So this is done here. Now once it's done, then we have to process the nodes in the reverse graph. Okay, so same story, whatever I did, right? I'm writing the same thing. While queue is not empty, all right, so here just poll the current node. Okay, queue dot poll. Okay, now in the result we have to add this result dot add this node. Okay, this is done. Then we have to just iterate over all the neighbors in the reverse. Okay, neighbor in the reverse graph. Okay, reverse graph dot get node. Okay, now we have to decrement the in degree of neighbors, in degree of neighbor minus minus. Okay, and if in degree of neighbor is going to become 0, then we have to add that in queue, otherwise not. Okay, in degree of neighbor, if it becomes 0, then in that case only we have to add that to our queue. Okay, neighbor. All right, and once this is done, okay, now we have to just sort the result to return the nodes in ascending order, because in question statement it is asked that we have to reverse the nodes in ascending order. Okay, so I'm just going to sort them. Collection dot sort result, and in the end just return result. Okay, so easy. Now let's run it and see if there are any code issues. We'll try to fix that. So all the test cases has been accepted, right? So now let's submit it. So see, our solution is accepted, right? So I hope that you guys are able to understand today's problem, and if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.